is velocity of the ball, and when you're talking about stocks, it's this thing that we saw called the velocity of the price, which means the rate of increase, which I'm not sure how you'd use that. And so you can take a mathematical, so what we're doing is we're taking something in reality and we're applying some mathematics to it, and then asking, what we get out of the mathematics, does that have any importance or meaning? So when you're talking about a ball and its movement, and you apply the concept of derivative, you get the velocity. That clearly has some meaning to us, right? Right? Velocity of a ball. Most people are comfortable with that concept, right? But when you're talking about stock, and you apply this concept of derivative to the price versus the time, you get the velocity of the stock price, but that doesn't necessarily mean too much to us, right? Now maybe if we thought about it more and more, maybe it would have some meaning, or maybe it wouldn't, right? So we can take a mathematical concept and apply it to anything, and maybe it'll come out with something that means something, and maybe it won't, or maybe it'll come up with something that means something, but we don't recognize what it means. But if we, put our minds to it long enough, it might actually be valuable. Okay? And the same thing with the second derivative, right? The second derivative, clearly we are comfortable with the concept of acceleration, right? But I'm not sure about the acceleration of the price of a stock, what that means, right? We don't have to just apply these to balls and stocks. There are many places where we can apply this to, right? Many, 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 many things. Many other things in finance, many things in economics, many things in psychology, many things in sociology, many things in geology, many things in every place, right? And sometimes it's going to have some clear meaning, sometimes it won't, sometimes it will be useful, sometimes it won't, right? We don't know, right? But we can go back just to the math and apply it to the picture, and when we did that, we saw that second derivative has something to do with the picture. That's a kind of still applying it somewhere. We're applying it to the picture, right? We're applying this concept of second derivative to the graph. So that's kind of still like almost an application, but it's a little more, it's within the field of mathematics. We didn't go out to finance, or we didn't go out to physics, right? Just within math, we interpret what it means. The second derivative means the concavity of a graph, but if you thought about it in terms of something else in math, it might have some other interpretation. Okay? So anyway, that's what the second derivative means in the graph. Third derivative, I don't know what it means. I'm not sure if there's a good, probably somebody has something about it, but I don't think it's not common, especially not in this level of course. Almost any level of course. Somebody might have studied it and might make some sense out of it, but not much. Okay? Okay, so now we have done, let's take a look at max-min 2. Okay, so here they want you to find the exact location of the relative and absolute extrema. So to do the relative ones, we've kind of talked about that. So we can use either the first derivative test or the second derivative test, right? Now it's a little bit harder here because this is a more complicated function. Okay? So this may not be the best problem to start with, but that's what this homework assignment is asking you. So it's a pretty hard, right? You have to find the first and second derivative of this. And that's not going to be a simple function. And finding, doing all the when is it 0, and when is it positive, and when is the second derivative, blah, blah, blah. Not going to be so straightforward for this function. This is not such a simple function. In fact, just to find the derivative of this, you have to use what? The chain rule, right? So just getting to the second derivative is hard, and then interpreting it is going to be troublesome. Okay? The idea, we did the very basic, and what we did is exactly what we want to do here, but each step is going to be more work. Okay? Understand? So what you should do actually before you do this is go to the text and read some easy examples first. Don't start with something like this. You'll just get lost, right? So don't do that. All right, but anyway, the idea is the same, but also we want to find the absolute extrema, which we really didn't methodically talk about how to do that. So how do you find the absolute extrema? Well, how about if the picture looks like this one here? Then is there an absolute maximum? No, because it's always increasing, right? And is there an absolute minimum? No, because it's always decreasing. However, if the problem said that we're only looking between 0 and 100, then what? Suppose 100 is over here. Then what? Then you could methodically go through and find out. Now it's possible that 0 goes down to here, but 100 is right here. Right, then what? Then this would not give you the maximum, the absolute maximum. This would be the absolute maximum. But if 100 was way over here, then, this would, at 100 it would be the absolute maximum, and this would not be the absolute maximum. Okay, so you have to think like that. Okay, that's what they want you to do. Okay, so you just have to think about basically you have to consider the endpoints as well as these points. Okay, and then you have to pay it, so you have to, like, one easy way to do it would be find the height here, find the height here, find the height here, and find the height here. And then is it higher here or higher here? Right? That's just like a straightforward, simple-minded way to do it, right? Okay? But anyway, that's the idea. If the endpoint was over here, this would be the maximum, but if the endpoint was over here, this would be the maximum. So you just have to determine that kind of thing. Okay? So that's called finding the absolute maximum. Okay? Any questions about that? All right? And as I said, these problems are much more troublesome to work with, though. So, okay, now let's look at the second one. Maximum, minimum 3, rather. Looks like the same problems. I know. These are dealing with E. So, you have to do the derivative of this one. And also log, which we didn't even get to yet. Okay, we didn't talk about the derivative of the log function yet. Okay, so we have to do that soon. And here, these are more like just pictures. So these you can probably do. Okay? And so after we get to that, I think there's one more section I need to add in here, and I also need to push some of these ahead a bit. But then we'll have a little time, probably, to do integrals as well. Okay, which is basically, in some sense, the opposite of derivative. What I mean by that is, You take a function and you take its derivative, you get a new function, right? If you do the integral of this function, you go back to the original function. Okay? So if you did, like, let me say that, like, suppose you start with x to the 5th, right? Take the derivative of that, you get what? 5x to the 4th, right? If you take the integral of that, you get back to x to the 5th. Okay, so it's like the opposite. Okay? So we'll learn about that. Well, it looks like we'll have time to do that. All right, so I'll spend a little more time on maximums and minimums next week. But we covered, what did we do today? We covered the first derivative test and the second derivative test. Okay? And they're both ways to get the local maximums and minimums. And then we also mentioned that you have to check the endpoints in order to get absolute maximums or minimums. Okay? So I guess that's all for today. And if you missed anything or you want to review it, you can check the videos on YouTube.